Wow, Ken, this simulator for the 1903 Flyer is so different from the simulator for the 1902 Flyer.
It really is.
Oh, thank you so much.
Thank you.
Okay, let's review. So far, we've learned how civilizations throughout history have dreamt of flight. We've seen how the engineering method can be used for solving complex problems and making dreams a reality. And you've applied a bit of the engineering method yourself by building kites and evaluating their performance. So what does all this have to do with NASA today? Well, Anna McGowan at NASA Langley Research Center in Hampton, Virginia has the scoop.
How can biology be helpful in designing aircraft?
What is the relationship between pressure and force? Why are the computer simulations important to the aircraft design process?
The Wright brothers discovered ways to sustain controlled flight. Today at NASA, the challenge is to research ways to make flight safer and more efficient.
One piece of research NASA is doing is called the Morphing Project. The Morphing Project is part of the next generation of breakthrough vehicle technologies. It's about designing the airplane of tomorrow and changing the world again in the process, much like the Wright brothers' invention changed the world they lived in.
We got the word morphing from the word metamorphosis. The word morph means to change, and we're using a lot of advanced materials and technologies to research how to make airplanes change from one configuration to the other. That's what engineers and scientists in NASA's Morphing Project are trying to do, transform the future of flight.
How are you transforming the future of flight?
That's a great question. The Wright brothers were inspired by watching birds soar,
and they designed their airplanes with wings that could manipulate the wind. The Wrights didn't use flaps on their machines like airplanes have today. In the Morphing Project, we were working on making airplanes as versatile as a bird is. So we're taking some lessons learned from nature, just like the Wright brothers did.
We're researching and testing many advanced technologies. One area is called smart materials.
We call these materials smart materials because unlike traditional materials, these materials actually move when you apply a stimulus like voltage or heat. They're similar to muscle tissue in this way, so instead of using complicated mechanical gears to move or control parts of future airplanes, NASA is looking at using these smart materials as future control devices on airplanes.
Another advanced technology that we're studying is called adaptive structures. In studying the structures for future flight, we're actually looking at technologies that can change the shape of parts of the wing during flight.
Why do you want to change the shape of the wings during flight?
Well, all wings must be able to adapt to different flight conditions.
Birds do this by gently bending and twisting their wings while they fly. In today's airplanes, we're using flaps and slats to adjust the wings to different flight conditions. In the future, we're hoping to enable wings to gently change shape in many different ways, similar to birds.
This is one example of an adaptive structure that we're working on. This wing changes shape for different flight conditions. It's designed very different than today's airplane wings. Today's airplane wings are typically hollow to hold fuel, and they're also very stiff.
This adaptive wing instead has a center spine to carry most of the aerodynamic load and movable ribs to change shape during flight. We design airplane wings using the principle of pressure. The following algebraic equation should help you understand this principle. Pressure is defined as the force divided by the area over which the force acts. The force in this case is the aerodynamic load. Have you ever popped a balloon with a nail? It's pretty easy to pop the balloon with one nail because the force applied to the balloon is acting over a very small area, only the head of the nail. This means very large pressure. Now, if you try to pop the same balloon with a bed of nails applying the same amount of force, you notice the balloon is very difficult to pop.
Why is that?
Because the area of the bed of nails is much larger than the area of the single nail. If we refer back to the equation for pressure, if you keep the same force applied but increase the area, pressure actually becomes much lower.
With this adaptive wing, we want to make sure the force, or the aerodynamic load, is distributed evenly across the wing, preventing the wing from breaking. We actually call this adaptive wing here the fishbone wing because it resembles the spine and ribs of a fish. To understand and design the fishbone wing, the engineers here at NASA use advanced computer simulations. These computer simulations help us understand the mechanics of the fishbone wing and tell us how the wing will perform in real life.
We are even looking at new ways to control the airflow over the wings of future airplanes.
The study of airflow is called aerodynamics, and today's airplanes use large flaps to control aerodynamics. For future airplanes, we're developing technologies that use very small devices to control the airflow on airplanes. We call this micro flow control. For example, tiny fluctuating jets that create a small plume of air on the surface of the wing can be used to make the flow smoother and less turbulent, and this reduces drag. By reducing drag, we can save on fuel costs and also reduce the amount of pollution coming from the airplane engines.
Here's an example of one of these jets. This device would suck in air and blow out air very rapidly to control the airflow over the wing. Now, several of these devices would be placed in a wing to control the airflow over an entire wing.
Even this example is similar to how a bird flies. In addition to twisting and bending their wings in flight, birds also rely on their feathers to adjust the airflow over their wings.
Finally, we're applying the principle of biomimetics in the morphing project.
Bio what?
Biomimetics is the abstraction of good design from nature. In other words, you look at how nature works for maximum achievement at minimal effort.
Today we're even examining the shape of fish fins because, in a way, fish are flying through the water.
Here are several examples of different fish fins that we're studying. We actually work with marine biologists to understand how the fish swim and how they're really efficient flyers. We also study seagulls. Seagulls can soar really well, and their unique wing shape is one of the many reasons they fly so efficiently. Here is an example of a wing that we would actually design for wind tunnel testing. We call this the hyper-elliptical cambered span because of the really unique shape and because we use ellipses to design this wing. In the morphing project, we take lessons learned not only from biology, but we also use a lot of advanced technologies, new math, new approaches, and new science to really make future airplanes even safer than they are today. We also want to make them more capable and able to fly in new and different ways. We also want to make them more efficient to help with pollution and also reduce the cost of flying. NASA's morphing project is looking to the future and trying to transform the future of flight.
Thanks, Anna. Now it's time for a cue card review. How can biology be helpful in designing aircraft? What is the relationship between pressure and force? Why are computer simulations important in the aircraft design process? If you're watching this on videotape, you'll want to pause the tape to discuss these questions. Okay, did you get all that? So far, we've seen how the Wright brothers began powered flight for humans, and we've seen how NASA is working to apply some of the early principles of flight that the Wright brothers perfected. You know, aeronautics sure has seen a lot of changes in the last 100 years. Let's visit Dan Giroux and his web domain.